Hello viewers, welcome back to my channel Computer Engineering Made Easy, and I am Anindita. In this tutorial we will be learning about the concepts of linked lists. We will also learn what are the advantages and the disadvantages of linked list over array. A linked list is a data structure that can be both linear as well as non-linear by nature. It is a dynamic data structure where each element is treated as a separate object. A linked list may have variable number of nodes and can grow as well as shrink as per the user demands. A single unit of a linked list is called a node. In most cases, it has got two parts. A data part where the actual information is stored in the node, and a pointer part which points to the next node in the linked list. A linked list looks somewhat like this. Here we have a variable called head which is a pointer to a node type of variable, and this variable is located in the stack memory. The variable head or the pointer to node head stores the address of the first node of the linked list. Each and every node of the linked list is created in the heap memory, and they are all linked to one another as shown in the figure. The first part of each node, that is the data part, holds the information, while the next part or the pointer part holds the address of the next node of the linked list. So therefore, we can redraw the structure of a linked list somewhat like this. Here, as we can see, in the stack memory, we have got the pointer to node called head, and in the heap memory, we have got the individual nodes which has got two parts. Say the first node has the address 100, while the second node has the address 500. This 500, that is the address of the second node, will be stored in the next part of the first node, indicating that the first node points to the second node. Similarly, let us consider we have another node, that is the third node, at address 300. So this 300 will be stored in the next part of the second node, indicating a link between the second node and the third node. Finally, let the third node be the last node in the linked list. Hence, we store null in the last part or the next part of the third node. Now, the address of the first node is always stored in the struct node pointer called head, indicating that there exists a link between the stack memory and the heap memory. This head is a very important node or very important pointer in case of linked list, as it holds the beginning of the linked list. If we somehow lose the value stored in this head, we will lose the entire linked list. If somehow the head of a linked list stores null, in that case, we consider the linked list to be an empty linked list, somewhat as shown in the figure. Now let us understand what are the advantages of a single linked list over an array. Arrays are static data structures. This means that we cannot alter the size of the array once it has been created. So for example, if we have an array of size 5 which suffices the current requirement of the user, we cannot increase or decrease the size of the array if a bigger sized or a smaller sized array is required in future. So what happens to suffice the need right now may not be sufficient in the future. So array does not provide that flexibility to adapt according to the requirement. Moreover, insertion and deletion operation in arrays are very costly. For example, if we have an array ARR of size 4 which has got the values 7, 4, 3 and 2 respectively, and here if we want to delete the value 4, what we have to do is simply copy the subsequent elements towards the in their left positions. So if we want to delete 4, it has to be replaced by the value 3. Similarly, 3 has to be replaced by 2, and at the end of the array 2 is still going to remain because we cannot delete anything from the computer's memory. We can only replace. So therefore, insertion at the same time will also be a costly affair because we have to again shift the elements in their subsequent positions to accommodate the new element. Another significantly large problem that arrays often encounter is the memory fragmentation. In memory fragmentation, the chunk of memory that we have gets fragmented over time as different sections of the memory are utilized by different processes. For example, say we have 70 bytes of memory. The first 10 bytes are free while the second set of 10 bytes are assigned to process P1. Again, we have got another 10 bytes free and the next 10 bytes are assigned to process P2. Subsequently, we have another 10 bytes free and the next 10 bytes are assigned to process P3, and then we again have 10 bytes free. So basically over here we have got 40 bytes free while 30 bytes are assigned to different processes P1, P2 and P3. However, these 40 bytes are not contiguous in nature. Hence, if we want to create an array of size 5 of type integer, then it will require 20 bytes of memory, and this 20 bytes has to be contiguous by nature. Now over here we have got 40 bytes of memory available, but we don't have 20 bytes contiguous. Therefore, we cannot utilize this memory to assign an array of size 5. On the contrary, we can use a linked list to assign these 5 nodes which will be located spread all over these 40 available bytes. This is where linked lists come to rescue. Even linked lists have their own set of restrictions. In arrays, we can access any element present in the array directly, whereas in case of linked lists, we have to traverse the entire linked list until and unless we reach the appropriate node where the value is stored. Hence, linked lists provide sequential access while arrays provide direct access. This is advantage of array because if we have to traverse the linked list in order to reach the desired node, the complexity of the code is going to increase. Whereas in case of array, since it allows direct access, the complexity will be big O of 1. Moreover, linked lists take more space than arrays. This is because apart from the data that it has to store, in case of linked list, each node also has to store the address of the node following the particular node. Hence, in case of an array, the example that we have taken, we have got 4 integer values, so the size of the array will be 4 into size of int, whereas in case of linked list, it is going to have 4 nodes, so the required memory space will be 4 into size of node. And by node we mean there will be one integer and another node pointer. Hence, the required size will be 4 plus 4, that is 8 per node, and the total memory space required will be 4 into 8, that is 32. However, in spite of these disadvantages, we still use linked lists because array require contiguous blocks of memory while linked lists does not. Moreover, linked lists can be categorized broadly into 4 groups. The first one is the single linked list or the singly linked list. The second category is the single circular linked list. The third category is the doubly linked list, while the fourth category is the doubly circular linked list. Now let us take a look at the first category, that is a single linked list. A single linked list looks somewhat like this, where the individual nodes are located in the heap memory, while the address of the first node of the linked list is held by a pointer type of variable, which is a pointer to structure node type of variable which is located in the stack memory. We usually call this variable the head. The singly circular linked list is somewhat similar to the singly linked list except for the fact that instead of the last node storing null in the next part, it stores the address of the first node of the linked list. The doubly linked list is however different. Here in the case of the doubly linked list, each node has got three components or members. The first one is the data member which stores the information. Apart from this, there are two pointers called the prev and the next. The next pointer, just like the single linked list, holds the address of the next node of the list, whereas the prev pointer is responsible for holding the address of the preceding node of the specific node. The last node's next part holds null, while the first node's previous part holds null. Here also we have got the head variable which stores the address of the first node of the linked list. The doubly circular linked list is also somewhat similar to the doubly linked list except for the fact that the next part of the last node of the list holds the address of the first node, whereas the prev part of the first node of the linked list holds the address of the last node of the list. The operations involved with a single linked list, or rather any of the linked list, includes creating the linked list, displaying the linked list, inserting elements in the linked list. Now, under the category of insertion of nodes in the linked list, we can have three different subcategories. The first one is the insertion at the beginning. That means we insert a new node at the beginning of the linked list. The second category is insertion at the end. That means we insert a new node at the end of the linked list. And the third one is the insertion in an intermediate position, which means we can insert a new node anywhere within the linked list except for the first and the last position. Now, insertion at an intermediate position also comes with three subsequent clauses. Here the user may want to insert an element at the nth position of the linked list, or the user may choose to insert an element before a node having value n, or the user may choose to insert a node after a node having value n. Apart from the insertion, the deletion operation is one of the major operations that are associated with the linked list. If the user wants to delete a node, this deletion can be categorized into three subcategories. The first one is deleting the first node of the list. The second one will be deleting the last node of the list, and the third will be deleting any intermediate node in the list. Just like insertion, deletion of an intermediate node from a linked list can also have further subcategories. A node having value n, or the user may also choose to delete the nth node of the list. Similarly, the user may also choose to delete a node before or after a specific node having value n. Each of these form different cases of deletion when writing the program to implement a linked list. Linked lists are also called self-referential structures. This is because a self-referential structure is a structure that has one or more pointers which point to the same type of structure of which it is a member. Since the next part holds the address of another node which is of the same type as this one, hence we call it a self-referential structure. The structure to define the node of a linked list will be struct node, int data, this particular member will be responsible for storing the data, and we will have a self-referential pointer which we write as struct node star next. Here this struct node star next will be responsible for holding the address of the next node of the linked list. Note that since the type of this pointer is same as the type of the structure within which it has been defined, we call this a self-referential structure. With that, we come to the end of our today's tutorial. In the next tutorial, we will see how we can implement the individual operations associated with a single linked list. Till then, bye bye.